Hi, everyone. Thanks for coming. I think I'll go ahead and get started. My name is Ryan Smith. I work for Wootric as a data scientist. And I'm here to talk to you today about transfer learning in natural language processing and how small teams with small data sets can utilize it to still build powerful models. So yeah, transfer learning in natural language processing. So what we'll be covering in this talk is first, we're going to look at a real problem that we at Wootric are solving using NLP and deep learning. And we'll go through a brief discussion of the methods we tried on our way to using deep learning to solve this problem. Next, we'll go into how transfer learning can help small teams with less data still compete with bigger corporations with established teams of data scientists. And along the way, we'll be looking at the results we achieved from applying these methods. So Wootric, who are we and what do we do? Wootric is a modern feedback management platform. We help companies measure and boost customer happiness. To accomplish this, we do three main things. So first, collection. We track customer experience metrics by gathering feedback. Next is analysis. We provide insights into what customers are talking about by classifying feedback at scale. And then finally, action. We help companies align around critical business problems identified through feedback and take action to drive growth and protect revenue. Now, the focus today will be on analysis, as where you could imagine most of the machine learning will take place. So the problem that we want to solve is that our surveys collect a lot of feedback, and we wanted to be able to deliver insights to our customers in an automated fashion. So two main questions that we are concerned with are first, what set of topics is the customer commenting on? So this is a multi-label classification problem. And next, how does a customer feel about the product or service? And this is your classic sentiment analysis problem. So here's an example of the dashboard we use to present these insights, just so that you're familiar with the problem that we're trying to solve and the insights that we're surfacing. So if you look at the top row, you can see a piece of text. This is a response to an NPS question, a Net Promoter Score question. And the customer said, enjoyed my first order. If nothing goes wrong in shipping, happy to recommend. So what we want to be able to do is to tell our users that this comment was about shipping and packaging. The customer had a positive sentiment overall. The sentiment related to shipping and packaging was neutral. And then on the left-hand side, you'll be able to see the breakdowns of various tags, which is what we call our labels that are being applied to each feedback, and how those breakdowns compare to each other. So naturally, the more accurate our prediction systems are, the less margin of error we're going to have around these breakdowns that we're showing to customers. And so in order to evaluate our models, we have to have a set of metrics that we want to benchmark them against. So this is precision, recall, and F1 score. Many of you may be familiar with them already. I'll just give a brief overview in case anyone is unfamiliar or hasn't touched them in a while. So precision is in classification, given that we've tagged a piece of feedback in our case, or overall just tagged a piece of data, how often are we correct? So this is a measure of every tag, how certain are we that that should be applied by our model. Recall is what % of feedback that we should have tagged, we actually ended up tagging. So this is more of a coverage metric that tells how much of the feedback we ended up covering. And then F1 score is just an easy way to combine these two metrics into one number. And so the equation for it is right there, 2 times precision times recall, over precision plus recall. And we'll be reporting F1 score when we report our results for our models. Now, our formal problem that we use machine learning to solve is, given a piece of feedback and its industry, what tags should be applied. We'll discuss this problem in general because it's a little bit easier to focus on, and then at the end, we'll round it out how we also incorporate sentiment analysis. So this, as I said before, is a multi-label classification problem. So to each feedback, we're going to apply a set of binary labels, which means that we're going to have a vector for every single possible tag that we could apply of zeros and ones. So each feedback could have 0, 1, or more feedback or more tags associated with it. Now, our metrics that we use are, like I said, precision, recall, and F1 score, but for each tag. Since for a classification problem, multi-class, you're able to combine these metrics together, but for multi-label, it's a little bit easier to see them separated apart. So now that we're applying machine learning to this problem, we have to decide how to go forward. So for business purposes, usually cost-efficient and time-efficient solutions are a little bit easier to implement and nice to start with. So I'm going to take you through our first approaches, which were using basic models and utilizing an existing service. So for basic models in NLP, the most basic model is bag of words. And it's very common because it shows good success and it's very easy to implement. So for those of you that don't know, bag of words is where you treat a document as a one-hot encoded set of vectors where each vector represents one word that's there. And so you have a set of sparse vectors that is just representing all your words, and you can combine these by usually adding them or just anding them together so that you have a 1 present if the word is there and zeros if it's not. Then you feed your resulting vector for that document into any kind of classifier that you want to. So a logistic regression model, SVM, or a simple neural network. And then that gives you your classification. Rule-based methods are what linguists usually come up with, or people with knowledge of the domain that you are predicting in. And so rule-based methods can range from very specific to very general. Rule-based methods are good because they are able to come up with very specific targeted solutions that meet your problem, but they also are time-consuming to make for each specific problem that you're trying to solve, and the more general they are, the more prone to error they usually are. Good things about basic models is that first, they give a good baseline so that you know how much effort should be put into improving your solutions. If you're trying a more complicated solution and not achieving that much better results or worse results than your baseline, then you know to shut it off from there, and it's not a good use of your time. Also, basic models, you can keep iterating, particularly bag of words, since you're just feeding a feature set into a classifier, there's still a lot of things to tune for that classifier. For instance, we were able to tune around our bag of words model logistic regression using class weights due to a class imbalance problem. And then finally, basic models require that you have a production system in place, which is always great to start with, even if you just have dummy data. But even having these basic classifiers will be able to show you if incorrect classifications or classifications you may not have been expecting will break your models or break anything about your pipeline. So here are the results we got from our first basic models. So on the left is the bag of words model. On the right is bag of words combined with a very general rule-based method. And the graph is showing an average F1 across all tags in our test data set for applying these methods. So problems basically are numbers, or actually, let me say what a good baseline would be, a good place to find where you want to achieve accuracy. So basically, we want to show what F1 score is good enough for us. And the higher our F1 score, the lower margin of error is going to be shown when we're showing aggregate metrics to customers. And so we see these basic models and we think we can improve upon them. And some of the reasons that our basic models don't do as well is language is hard to model. You're here for an NLP talk. I'm sure you have encountered problems before where people say certain things that do not translate well to basic models. So for example, the engineering cost to implement your product was too high. People are talking more about manpower and less about actual pricing of your service. And so a bag of words method would mistakenly tag this as price when in fact it should be about something else. And this leads us to bag of words and rule-based methods can certainly be improved upon. So the other very easy system to set up is use an existing service that predicts what you're trying to predict. So we started with this. We used Google Prediction API, which was around about 2 years ago when we started looking into this problem. Had a very easy interface. You would send in a CSV with a piece of feedback labeled, and it would tell, using a giant training set, it would just give you a model that you can then query to find your predictions. It had binary or multi-class options. For us, we used a set of binary classifiers, which ended up being a little more expensive than we had hoped because it was a set of a bunch of different models for every single piece of feedback. But it did give better results than our basic models. So A, it passed the baseline, which is great, and B, it was giving solid results. Problem with it was that eventually Google deprecated it. And a couple months before that, it started failing regression tests. We looked into it, thought, why is this acting so weird? And then a month later, oh, hey, we're not going to continue this service. So this is one of the problems with black box models is if things go wrong, you have no control over it. Google eventually came out with AutoML, but this was, I think, a year and a half later, and we needed something now to improve upon our basic models. So we thought about deep learning. So deep learning's fun, as we all know, but it's relatively time-consuming, and you want to make sure it's worth it before you invest the time and effort to implement it into your pipeline. So that being said, there are, for example, great packages today like Keras or PyTorch where you can very easily implement basic deep learning models, but usually they require a lot of data. So we used a basic convolutional neural network and LSTM, which is a recurrent neural network, models on our limited training set. The CNN did very well, or did better than our baseline. The LSTM was not effective. And here are the results from that. So you can see we showed a little bit improvement, including the CNN into our set of models. The reason the LSTM did so poorly and the CNN didn't give us a huge result increase over our existing models is that we have small training sets. So part of our problem is that we have many different industries that we are focused on providing tags for. And to be able to quickly add industries, we need to be able to manually label this data quickly. So usually we hover around 1,000 to 2,000 rows of feedback being labeled for our problem. Now, manual labeling is time consuming, and it requires domain knowledge about the topic you're labeling about. So general things about price or if somebody's asking for a feature are usually pretty easy to label. But if it's a little bit more specialized, for example, some of our customers are in the financial sector, you usually need a little bit of domain knowledge to tell if people are talking about various trading terminology and other things there. So we also have a class imbalance problem. A lot of these tags that we apply only show up in 5 to 10% of the feedback. This becomes a problem when every incremental 1,000 rows of feedback you add only has 50 rows of the tag that you're trying to apply. And so only 50 examples of the classifier to learn from. So this leads us to how can we learn from so few examples and still compete with companies that have hundreds of thousands of feedback to train their models and the employees to tag them. Enter transfer learning. So transfer learning, the whole point of it is to make as much use of as much data as possible. And so basically, if we have models trained on data that seems uncorrelated to our problem, we still want to be able to take advantage of them to train our specific classifier. So this is the general pipeline for transfer learning. We start with a general data model that learns from usually a much larger set of general data and then gives us some unrelated output. And then we have a task-specific model that is trained on our much smaller set of tag data and then gives us our task-specific output. So usually that unrelated output is not helpful to us. We want to find a way to then bring it over to where the general model feeds into our task-specific model and can influence it to improve our task-specific output. So more data is better, and how do we utilize it? Some common techniques right now to make the general model feed into the task-specific model include using parts of ImageNet models, which was a huge improvement in computer vision in 2016, using prior distributions for Bayesian analysis, which is where you, from your own knowledge of the domain, can superimpose a distribution onto the problem that you're trying to solve. And then in NLP, we have word vectors, and then within the last year, language models being used as transfer learning methodologies. So we'll start with transfer learning in computer vision. ImageNet was a huge advancement in the field of computer vision. And so what ImageNet is it's a very large database of labeled images where there's many different labels and many different subsections of images that you can look into. And one of the things that people found when training models across this huge ImageNet database was that convolutional neural networks tended to learn lower level features in the lower layers, and then higher level features such as edges, shapes, and colors in the beginning layers of the model, and then the later layers would be more tuned towards that model's problem that it was trying to solve. So this is kind of like saying that I have a huge database of images that are all labeled for cats and dogs, but then I want to be able to apply that knowledge to still labeling things like tables and chairs. What will happen is that the model trained on a huge database of images will learn these things such as edges, shapes, and colors, and then be able to transfer that knowledge to also applying it to the tables and chairs dataset. So here's a very dumbed down example of a transfer learning being applied in computer vision. So say we have a very large database of fruit classification. And so we have this fruit classifier that learns what apples and various other fruits look like. The beginning layers of the model will learn about edges, shapes, colors, and then progressively get more fine-grained until it arrives at a fruit classifier that can tell apples from oranges and pears. What we want to do is to train a vegetable classifier. However, our vegetable data set is much smaller. What we can do instead is take that same base model that knows about edges, shapes, colors, so the first two layers there, and then cut off the part that is actually a fruit classifier and put on an empty, uninitialized classifier at the end. And what we can then do is train our new model on a much smaller data set. So this helps because what's happening is we're reducing the feature space of the vegetable classifier from a totally pixelated RGB values image into instead some vector that represents edges, shapes, and colors. And so this lets us learn a lot more quickly about what types of things will lead to being a vegetable or one type of vegetable over the other. Obviously, this is a very simple example and not totally representative of what happens. A lot of the time, it's not very obvious what layers of your model are actually pertaining exactly to your problem and which ones are super high level. So that's a huge area of focus of trying to investigate that and figure that out. So that is transfer learning in computer vision. Now transfer learning in natural language processing. So the first thing that came out was 2012, people found word vectors. There was a very big paper published by Google, I believe, that was a huge stride and really helped natural language processing models improve. And so what word vectors are basically encoding a word instead of in the bag of words format of a one-hot encoding into a smaller n-dimensional vector, which can then be applied to a machine learning model in the same way as bag of words or into a long short-term memory model or other recurrent nets to learn things about your data set. So word vectors learn one initial layer of a model, which is the embedding layer usually, and they usually only capture one aspect of language. So for example, your words for word vectors are always going to have the same vectors no matter of the context that they appear in. And then good advantages about word vectors are that you do not need labeled data to train them. They train over any corpus of text. So all you need is the text and a few parameters to set when training them. And then they also led to things like the infamous Google News generated word vectors, which was a public data set of, I believe, 3-point-something million word vectors for people to use that had been trained over a large corpus of Google News articles. So word vectors were great, but we wanted to improve on them. And so in the last year, language models became a source for transfer learning in natural language processing. So what a language model is a way to predict what words will be mentioned next in a piece of text. We'll go over that later, but the main parts about language models are that they learn multiple general purpose layers. So a language model can be an entire model as opposed to just an embedding layer offered by word vectors. So a language model is trained to model language and not just words. So in this example, we have the two pieces of feedback. I hit the ball, and our website got a lot of hits. For word vectors, these will both be modeled, the word hit will both be modeled by the same vector. But for a language model, because it has multiple layers, we're able to differentiate what vectors will show up from the result of this language model based on the context around those words. And also, like word vectors, another great thing is that you do not need any labeled training data when training a language model. So here's the what is a language model brief or simple demonstration. So basically, a language model seeks to predict the next word in a sequence at each point of the sequence. So in our example right here, we have the classic NLP sentence of the quick brown fox jumped over whatever. And what we want to do is at each word in the process, predict what word will come next. So we start with a beginning of sentence label, and then we send it into a recurrent layer, which then feeds into a softmax layer, which then gives us a distribution of what our predicted next word is. We train the first part of the sequence, expecting the word the. Then, in the next input, we input the and train it to expect quick. Then we input quick and train it to expect brown, and so on. So one of the great things about language models, like I mentioned, is that you do not need labeled training data to train them. This is because all you have to do is feed in an existing corpus of text, like a giant database of Wikipedia articles or the Penn Tree Bank, and you can quickly be able to model and predict what words will come next in that text. So language models are usually thought of as encoder-decoder architectures. There's other ways to go about this, but this is kind of the most basic way to do it, especially from a deep learning perspective. And so the encoder part is usually all the recurrent layers that you feed in from the beginning. So after the embedding, which will usually occur in the input part, you would have the recurrent layers acting as the encoder, which then feed to a softmax layer or layers which act as a decoder, and then they will give you your distribution over possible words on the output. So there's many different ways to go about this. One of the cool advancements last year was freezing the decoder layer to be the same as your embedding layer so that the encoder was really doing all the work. And so what we can do using these encoders and decoders is kind of a similar thing to what we did in the fruits and vegetables example. So you have a general corpus that you're inputting into your language model. So this general corpus could be anything like a giant Wikipedia data set, the Penn Tree Bank, a Twitter stream, whatever. And basically, all it's learning to do is model that language and predict the next word at each sequence of the input. So you have the encoder and the decoder present in that model. Then what we can do is we can remove the decoder and put on our own uninitialized classifier that we then train on our much smaller data set. So the great benefit of this is that the encoder already has a lot of the intricacies of how language is used, and then we can learn from a much smaller feature set for our task-specific classification. So overall, the main thing from language models and using them in transfer learning is that you want to initialize your model state with the encoder of a general task language model. And so you can iterate this process if necessary. What that means is that we can start with a giant overall model of how human language works, so the language that you're modeling specifically, say English. You can start with just a giant trove of Wikipedia articles written in English. And then you can take a set of unlabeled, just straight text from your own domain that you're trying to solve. So for us, that would be customer feedback, and train that language model more on your domain of text. Then What you do after that is the same process as before. You put on a classifier at the end. But so basically, you can keep making your language model as specific as you want on decreasing sizes, but more increasing specificity of corpuses of text. So this has been commonly referred to as NLP's ImageNet Moment in a great paper by Sebastian Reuter that came out a few months ago. And the headline of that is that finally, starting in 2018, we can use transfer learning to quickly productize deep learning models for NLP. And the reason we can do this is that we can quickly make use of publicly available text. Here are some examples like Wikitext, the Penn Tree Bank, Twitter Stream, or even, as a recent OpenAI paper proved, a random web crawl across the internet modeling how humans use language. And even some models are available. I believe Salesforce has an AWD LS TM that they trained over the Wikitext 103 dataset. And you can just download that and remove the decoder part and start your classifications from there. So our transfer learning model was also modeled over Wikitext 103. Like I said, there's pre-existing versions of these. We trained our own. And then what we did after that was we refined that language model across a domain or a corpus of our customer feedback in order to tailor it to our domain. And then we, at the end, took off the decoder and put on our own classifier and trained it for each of our industries over that smaller task-specific training set. And here are the results from that. So we showed a 17% improvement over our basic methods, which felt very gratifying, and we kept kind of a linear growth, which is I haven't really seen before in machine learning from all the different the different methods that we tried on the way to this. We usually saw a little bit of logarithmic growth. But so this was a great improvement, and it really made us feel validated that we pursued the transfer learning approach. But we did want a comparison still. So AutoML came out about 6 months after we implemented this into our production pipeline. And we wanted to see, okay, well, Google probably has it figured out pretty well. Let's see how we compare to what they've done. So we trained AutoML on our own data set, and we actually achieved 8% improvement over their average F1 score on our test set, which felt very validating. And further, we then used our transfer learning approach on our sentiment model. If you remember from before, I said we wanted to see how customers feel about the product or service they're being offered and each aspect of that service. So we use our sentiment model when determining aspect-based sentiment analysis for our tags. And our sentiment model was actually trained on our much smaller data set of customer feedback reviews in order to get our positive or negative scores. And we actually achieved 96.5% accuracy across our test set in comparison to 92% accuracy for Google, which also felt great and goes to show that using transfer learning especially, just because Google is Google doesn't mean you can't beat them in your own domain. So those were the main improvements that we made over our models and the main benchmarks that we reached. So just to summarize some of the stages of the talk, steps to take when you're implementing deep learning or solving a machine learning based problem. First, evaluate if you do need deep learning and transfer learning, because it's always good to pursue other methods that may be simpler and easier to implement. And then if you do find that you need to use deep learning, transfer learning is a great place to start in NLP because we often have access to general, unspecific data that we can then train a language model on and refine to our specific problem domain. And then finally, language models are a great improvement, but NLP is still not near computer vision in terms of accuracy. And so there's still room for improvement over language models in the transfer learning space. And because of this, you want to make use of as many building blocks that can transfer and abstract your data prediction out across those as possible. And maybe you'll find the next big moment for NLP. And yeah, here are some references. So the paper I mentioned before, NLP's ImageNet Moment has arrived by Sebastian Reuter. And the paper that actually turned us on to this method of transfer learning a couple years ago, or a year ago when we implemented it, was Universal Language Model Fine-Tuning for Text Classification. Both of them are great reads, and I would very much recommend reading those. And yeah, that is about it. Thank you for coming. And if you have any questions, feel free to ask them.
Hi, great presentation. Thank you. I was just wondering, is there a lower bound to the dataset size where this stays effective? Like
For the general unspecific corpus or for the task-specific data?
for the task-specific data.
So there's always going to be a lower bound, and it's going to depend greatly on your data. So for us, like I mentioned, we have a class imbalance problem, which means that sometimes we only have tags show up in 5 to 10% of the data. Because of this, our lower bound we found was much lower than they mentioned in the paper. So the universal language model fine-tuning paper used a balanced sentiment dataset to conduct their research, and they found that they were able to achieve similar results to an LSTM over all 200,000 parts of that dataset with only 200 rows of the sentiment, labeled sentiment data. And so the lower bound is obviously going to depend, but with transfer learning and findings from that paper, we found that it's much lower than using classic deep learning methods.
I'll ask a question. You mentioned the F1 score improved. Would you say that your customers noticed? Was there a product implication to that?
This was actually, we did not have this exposed yet, so we actually just released this service. We call it our CXI, CX Insight service. We just released that recently, and we actually only had one customer before we implemented the transfer learning approach. They, to be honest, weren't totally paying attention that much to their changing things, but what we found was that we were able to provide a much smaller margin of error with this change in accuracy, which was great. That's a whole nother talk that I could get into about determining margin of errors from classifiers. But the improvement in F1 score, specifically how it was an 8% improvement over Google, really allows us to offer a smaller margin of error than if we had used them, which was very rewarding.